I won't let you use the whole packet, but I will let you use review for this test that I'm going to give you. And it's pretty short. There's almost nothing on parametric equations in delta math, so everything's going to be on paper. So this is actually going to be a paper test coming up. But it's 2 pages. It's short. Yeah, it's short. And that's not multiple choice, in case you were curious. It's not multiple choice. Yeah, no. I haven't done multiple choice tests since 2020. All right. So this whole unit that we've been working on, Unit 7 here, is polar and parametric functions. And so we're into the parametric side of things. And so we've been accustomed to having equations where we just have like y equals 3x plus 7. A single equation with one independent variable and one dependent variable, and we just graph it on our xy coordinate plane. And those are called rectangular functions because they graph on our rectangular coordinate plane, our xy coordinate plane. Hi, oh, thank you. That's heavy. Thank you so much. Appreciate it. A saxophone. So, all right. So, you're pretty good at functions, rectangular functions, regular xy functions. But what we're going to look at today are parametric equations, and parametric equations are equations that have 2 dependent variables, and we use them a lot for things like that describe how things move. And so this is a really good example to get started. That's why I wanted to do that. When we talk about how things are moving, we can talk about, like, if we're throwing a football, we can talk about how horizontally it goes, how far away does it go, so that's the horizontal distance that it goes. But we can also ask the question, well, how high does it go? And so we have, typically when we use parametric equations, we're talking about a horizontal distance and a vertical height that it might go. And what we do is we put these 2 things together and form a parametric equation, like a pair of equations, okay, to represent the movement. And so a baseball is thrown in the air. The function x of t equals 40t represents the horizontal distance that the ball has traveled after so many seconds. So this graph looks like this because it's thrown really fast, and it's just thrown, and all this is showing is that at 0 seconds, it's 0 feet away. It's right in the pitcher's hand. And then after a very long time, 4 seconds, that's a long time to throw a baseball. I'm sorry. But after 4 seconds, evidently, that ball is 100 and, God, I can't even read that, you guys, 160 feet horizontally away, like that, way over there, seconds later. And so that's what that's showing. Now, over here, the function y of t equals negative 16t squared plus 48t plus 64, that's this equation here, represents the vertical height of the ball. And so, oh, this is interesting. So this graph is saying, hey, at 0 seconds, the height of the ball is way up here at like, oh, not quite 70 feet. So maybe they're up on top of a hill, who knows? Okay, but they're 70 feet above, and they throw the ball. And at 1.5 seconds, it's 100 feet high. So they really whipped that thing really high, got 100 feet tall, and then 4 seconds later, it landed the 70 feet below, okay, back at the ground, all right? So they really flung that thing out there. And so that just measures how high the ball went vertically, all right? What we want, though, is to put these together. And so we're going to show these. To show both the vertical height and the horizontal distance, we can use a parametric equation. And again, a pair of equations so two equations, basically. If x and y are continuous functions, then the parametric equations are defined as, well, x equals x of t, and y equals y of t. T is called the parameter. We might also see it written this way, where we have this greater function, and we have a function in place of the x, and we have a function in place of the y. But it's basically giving you a new ordered pair. Okay? And so we can graph these and create a parametric curve, and it's actually pretty easy to do. So we're going to write a set of parametric equations for the scenario above, and then complete the table and sketch the graph. So our parametric equations are pretty easy. I'm just going to write x of t equals 40t, and y of t equals negative 16t squared plus 48t plus 64. So we could write it that way. And then what we're going to do is go ahead and just plot some points and sketch the graph. And we're going to start, these graphs started at time of 0, so we're going to start at a time of 0, and 1, and 2, and 3, and 4, and all we're doing is plugging in our values. So guess what? We're going to review a fun thing to do on your calculator. So in your calculator, well, we can do the x's really easily, but we'll do it with the y coordinates. I'm going to take 0, and I'm going to plug in that t value. What is 40 times 0? And what is plugging in a 1? 40 times 1? 40. And 40 times 2? 80. And 40 times 3? 120. And 40 times 4? 160. So that was an easy one. We're going to use our calculator to help us out with this one because that's going to be a little more challenging. So what I want you to do is, are you in function mode? Make sure you're in function mode. And then go to y equals, and we're just going to go ahead and type in negative 16t squared plus 48t plus 64. So I'm just going to insert the equation in y1, and then we can use function notation to evaluate this in the home screen. So once you get that equation in there, go ahead and do a second quit, and go back to your home screen. And we can call up that y variable pretty easily by doing a alpha F4. Alpha F4 pulls up our variables, all the y variables, and we want that first one, we want y1, so just hit enter. And I want to do y of 0, and it's 64. And then I want to do alpha F4 y of 1. And so what it's doing is it's actually plugging it into the equation for us, and we get 96. Super good. It's so easy. This is a great, great thing to be able to do. And then I want y of 2. Oh, that's also 96. That's interesting. Y of 1.5 is 100. Oh, that's interesting. All right, cool. And then y of 3 is back down to 64. And then y of 4 is, whoops-a-daisy. Oh, Jesus. Y of 4 is back down to 0. All right, are you getting it? Did you have a question, Karen? No, my bad. You got it? Okay. Okay. Is that pretty cool or what? I think it's pretty good. Okay. And so now all we have to do is actually plot the xy pair. And so we're plotting the x and y coordinate. Let's see. Ooh, I guess I have to create this. So our x values go on my x-axis. They go from 0 to 160. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, hey, look at that. I guess each one is going to be 10. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 120, 30, 140, 150, 160. Okay. And then, oh, probably these will be by 10 as well. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. There's 100. Okay, that'll work. All right, so I'm going to plot these ordered pairs, essentially the x comma y that we just create. So 0, 64 would be about like right here. And then 40, 96 is like about right there. And then 80, 50, 60, 70, 80, and we're at 96 again. And you said in between those we got up to 100, so it goes up a little. At 120, I'm at 64. Yep. Thanks. And then at 160, I'm back down to 0. And so the x comma y, this represents the combination of the horizontal and vertical components of how the ball traveled over time. And so we can connect them sort of with a nice sort of curve. We can also show the flight path where we put little arrows on our curve to show the direction of the movement. All right, and so this usually we would label like t equals 1. This is at time t equals 2. T equals, oh, this is t equals 0 rather. 0, sorry, 1, 2, t equals 3, and t equals 4. So we can show how the ball moves with respect to time, horizontally and vertically, which is kind of cool. So what this represents now, on our horizontal axis, this is the horizontal path of the ball, and this is the vertical path of the ball with respect to time. So it's really a combo graph, so to speak, which is kind of cool. All right, questions on that? Pretty easy, not too bad. All right, turn the page. So I basically already talked about all that already. So parametric function as a function that has an equation for the x-coordinate and a separate equation for the y-coordinate. So we would typically write this as, here is an equation for the x-coordinate, and we have an equation for the y-coordinate. And when we put those two equations together, we form an ordered pair. T is called the parameter. And at any time t, we know the coordinate point of f of t by substituting values of t into each equation. So that's all we have to do. So at time t equals 1, where is the parametric function f of t equals all of this? What do you suppose we need to do? Yeah, plug it in. So this first one, I would call this x of t, and the second position here is y of t. So I want to find x at -1, and so all I'm going to do is plug in my -1 for t. So 6 minus the -1 squared. Be careful, make sure you use parentheses correctly. What is -1 quantity squared? +1. So this is 6 minus 1, which is going to give me 5. And then y of -1, so I'm plugging it into the y equation. So -1 plus 3 is 2. And so at t equals -1, the f of, well, I'm going to write this. I'm just going to write f of -1 equals 5, 2. I don't need to write at t equals -1, it's redundant. So that is the position where the curve is at -1 for time. So that's easy, just plug your stuff in. All right, good. So same thing here. We want to create a numerical table. What do they want us to do? Plug it in, plug it in. All right, and so again, here is our x of t, comma, y of t function. And So this is the stuff you want to be able to do pretty easily, but we're going to take our -2 and plug it in. I'm just going to start with the x of t equation. So -2 times 3? -6. Ooh, a little bit harder. What is 3 times -3 halves? -9 halves. You go straight across. -9 halves. All right, straight across. 3 times -1? -3. What's 3 times -1/2? -3 halves. Very good. 3 times 0? 0. 3 times 1/2? 3 halves. 3 times 1? 3. 3 times 3 halves? 9 halves. And 3 times 2? 6. Very good. And again, don't be scared of fractions. You do have to know how to do this for all my juniors. You have to know how to do this for next year in calculus, okay? You've got to be able to work with fractions. It really makes life easier because you have that no calculator portion of the test. So, yeah, no calculator. Okay. All right. So second equation is t squared minus 1. And so I'm plugging in -2 squared minus 1. What is -2 quantity squared? 4. Minus 1? 3. Good. Now we're plugging in -3 halves. So -3 halves squared minus 1. Now this is a tricky one. This is a good one to know how to do. What is -3 halves quantity squared? 9/4. Positive 9/4. And then I have to subtract 1. -4/4. Very good. -4/4 gives me 5/4. Very good. All right, so 5/4. All right, what is -1 quantity squared? -1? 0. All right. And then we're going to have -1/2 quantity squared. 1/4 minus 4/4 -3/4. Very good. Plugging in a 0. -1. Very good. 0 squared is 0 minus 1, -1. And again, plugging in 1/2. 1/4 minus 4/4 -3/4. Again. Plugging in a 1. 1 squared minus 1 is 0. It is 1/2 being squared. Yeah? Good. Okay, good. All right, so we now have plugging in 3 halves. What is 3 halves squared? 9/4 minus 4/4 is 5/4. Very good. And then 2 squared is 4, minus 1 is 3. So you can see there's some repetition there, but being able to work those simple fractions is a really good, absolutely necessary skill, particularly for my math students for next year. Okay. So let's look at the graph of that same parametric function, and we're going to use the table of values to plot the points in order from the lowest value of t to the highest value of t. So we really just want to plot the ordered pairs. So we're going to plot -6, 3, 1, 2, 3, 4, 5, 6 is out here, 3, so that's fine. Plot that a little bit off the graph, totally fine. Where's -9 halves? No. -4.5, yeah. -4.5. 1, 2, 3, 4, -4.5. And where's 5/4? 1 and 1/4. Very good. So just a little bit above 1 there. -3, 0. Where's -3 halves? 1, -1.5. Very good. And down 3/4, so that's 0.75.
Please excuse the interruption. At this time, please release the varsity baseball and softball teams. Thank you.
Goodbye, class. It was fun. This is all you're doing. It's like super. Yeah, it's attached in the packet. Yep. There goes the class. Good luck, you guys. All right, we got 0, -1. We got 1.5, -3/4. We've got 1, 2, 3, 0. We've got 4.5 and a little more than 1. And then we've got 6 up 3. Now, we want to connect these points in order. So, in order that we made them. And then, we also use arrows to indicate that direction of motion. So you can put the little arrows that say, hey, we're moving along this direction. All right, any questions on that? Good, perfect, turn the page. So that graph had no restriction on the domain. There was no restriction on the time parameter. So this graph technically will continue on both ends. So we really should, on that graph, go ahead and extend with arrows because it really would continue because there was no say, hey, we only want time between 0 and 4 seconds. That's all we're interested in. So this didn't have that sort of restriction. So that curve would continue forever. But sometimes we have restricted domains, which you can see here's that sort of restriction on T. So restricting that time parameter. We have a starting and an ending point for motion along that path. And so because that parameter is on there, we're only interested in the time values between -2 and 3. So let's go ahead and plot those points. So 0, 1, 2, -3. And then -3, -1.5. We have -4, 0. We have -3 up 1.5. We have 0 up 3. And then we have 5, 1, 2, 3, 4, 5 up 1, 2, 3, 4.5. And again, we're going to connect these points from the first point, the leftmost parameter. So from this point here, and we're going to connect it like that. The beginning of the graph is at what point? 0, -3. Good. The end of the graph is at 5, 4.5. And again, we can still use little arrows to indicate the direction of motion, but we're not going to put continuation arrows because this has that restricted domain. So it literally starts here and ends here, and that's it. Can you handle it? Do you have any questions for me? Okay. That's it. The rest is the practice, and you can find the solutions